There's no quantum without nano, there's no nano without quantum. They're all intimately related. And to understand one or do one, you have to also understand and do the other. We develop and apply sensitive, high-resolution tools for magnetic imaging. We study small magnets. We study small mechanical objects. We're generally interested in pushing the limits of how sensitively we can measure things. As you make things smaller and smaller and more sensitive, you start to get into the nanometer scale and you start to notice fluctuations. First due to temperature, then at the smaller scale due to quantum mechanics.
So my team works in the field of nanophononics, and this is the field in which we try to control phonons nanostructuring the materials. Phonons are vibrations of atoms in a solid, and they are carriers of heat and sound in materials. So in particular, within my group, we work quite a bit on thermal management. So we design two-dimensional heterostructures and heterostructure in nanowires, which are filamentary crystals, in order to design the thermal properties of the materials, in particular to remove the heat as fast as possible, for example, from electronic devices, or to remove the heat in specific directions. Nanoscience is at the core of nanophononics, as also the word suggests, because in order to control phonons that are responsible for carrying heat, we have to structure the material at the nanoscale.
We study quantum effects in nanomechanical structures, so little vibrating structures such as those that are used in atomic force microscopes and other sensors. And we use laser light to control their vibrations and to read them out with great precision. And we want to put them in strange quantum states to enhance the performance of such sensors. So we use techniques of nanoscience to structure, to pattern these nanomechanical oscillators to give them extremely good mechanical properties so that they can vibrate for a very long time without decaying to the environment. And for this we use the tools of nanotechnology.
So we search novel materials for quantum computation. We put molecules on superconductor which form a topological superconductor which could become a new platform for quantum computation. So we use nanoimaging tools such as the scanning tunneling microscope and the force microscope to determine the structure of the molecular layers and also to determine electronic and magnetic properties of those systems.
We are studying the fundamental physics of single spins in semiconductors as a basis of building future quantum bits, qubits. We are using both electrons and holes and also look at different materials, silicon or germanium. Since these are standards in the industry, we can do excellent nanofabrication with these, and also they can be very high quality hosts for high fidelity qubits. Nanotechnology and nanoscience plays a key role in our research because we need to produce and analyze and image these structures which are the hosts of our qubits. These are very small structures in semiconductors typically. They are on the kind of nanometer, 10 nanometer, 20 nanometer length scale, and we need to use advanced fabrication methods as available in the Swiss Nanoscience Institute to produce these structures.
We measure transport of electrons in semiconductor devices. And with these measurements, we want to understand the properties of the semiconductors. And the aim is to use these semiconductors and to build qubits, the smallest entities of a quantum computer. We have 3 projects in our group. One project is about investigating whether single electrons in germanium can be used for quantum computing. One project is a different approach, also to build qubits. It uses superconducting Josephson junctions. And the third project is about using graphene as a material and study whether we can use electrons in there to build qubits. We study single electrons in our semiconductor devices, and in order to study these single electrons, we need to confine them into very small cages. To build these cages, we use lithography at the nanoscale. To do this, we require a clean environment as it is provided in the nanofabrication lab.
So to sum this up, if you want to use quantum mechanics for something useful, like building a quantum computer, we have to catch and manipulate and store small objects, for example a single electron. To do this, we have to fabricate tiny structures, typically on the scale of tens of nanometers, and that's exactly where nanoscience and nanotechnology become indispensable for quantum technology.